Hello, this is the next video in a playlist that I'm calling Parameter Estimation, and we're going to look at sufficient statistics in this video. So let's let x1 through xn be a sample that's IID from this density or probability mass function. A statistic is any real valued, or it could be real vector valued, function t, and written like this to imply it's a function of the data, sometimes written in vector notation, and sometimes slightly abused notation, just t. But appreciate that all these are a function of our sample. For a vector valued function, each component of the vector is a statistic. They don't have to be the same function. Now, the idea of sufficiency is to reduce the data with statistics such that no loss of information occurs when estimating the unknown parameter. And here's a simple example to illustrate what we mean by that. So let's flip a weird coin n times, and let's let xi be the result. It's a 1 if it's a head and a 0 if it's a tail. And so this is a Bernoulli distribution. And so the joint distribution is the product of these n times, which you get this. Now let's let t, our statistic, be the sum of these xi's. And what this represents is it counts the number of heads that we flipped in tries. So our estimate of the probability of a head is 1 over n times this sum. Now the question is, do we need to know each xi? So do we need to know where the 1s and 0s occurred? Or is it sufficient to really just know the sum of the xi? So how many heads did we occur? And by only knowing this sum and not knowing whether each one was a 0 or a 1, aren't we estimating the probability of a head the same? We're losing no information on this estimate if we reduce that sample to a statistic, the sum of the xi. And that's what we mean by sufficiency. Now, a little more technical term or definition of sufficient statistic is this. Let's let xi, I from 1 to n, so it's a sample, be IID from this function. Of course, the unknown parameter theta lives in the parameter space omega. Let's let t be a statistic. T is sufficient for theta if the conditional distribution of our data, given the value of this statistic, is independent of theta. And so really what this means is once we know the value of our sufficient statistic, knowing the rest of the data doesn't help us estimate theta. So we've taken our data of size n and reduced it to a number. And that's sufficient. That's all we need to know to estimate this theta. We're not gaining anything by knowing the actual values of our data. Now let's look at an example. Let x1 through xn be IID Poisson with unknown parameter lambda. So the probability mass function is this. The joint probability mass function is this. It's the product of this n times, and we get this. We want to show that the sum of the xi is sufficient for lambda. And here is how we show it, based upon this definition. Oh, up here. Here. I'm looking through a little 2-inch screen. So the answer is let t equal this sum, and say it equals value little t. Now we know since capital T is the sum of independent Poisson random variables, it's also distributed with a Poisson in lambda. Now the probability mass function of our statistic is this. It's Poisson, where this is the parameter in lambda. And one big note though is that this is over all xi, but such that they have to sum to t. So it's really not all the original, our domain is not the original. There's a restriction that it has to sum to t. And that's actually a pretty important point when we talk about auxiliary randomization in the next section, or the bottom of this page. So here's the conditional distribution, x given our sufficient statistic. And this is where, for all x's that live in this set A, which is all the xi's such that they sum to t. Okay, so this can be written as, just using probability theory, f of x given lambda divided by f of t given lambda. And then this was a Poisson, and this was a Poisson. And now we cancel. This cancels, the lambdas cancel. Well, and that's because this has to sum to t, right? And then these don't. So we get this. Now note that this is independent of lambda. There's no lambdas here. So thus, the sum of the xi is sufficient for lambda. So we can reduce the data to this sum, and then we can estimate lambda the same as we knew all the data. Now, auxiliary randomization is this. If we only know the sufficient statistic t, can we randomly generate data, call it x star, that has the same distribution as x? And the answer is yes. And then we use this conditional distribution to generate data, right? So here, there's no unknown parameters. So everything here can be known, and we use this to generate that random sample. And so here's a little proof of it. So let's say that we have some distribution function for x star, and this is equivalent to if the joint density of x star and t equals little t, right? So remember, this is restricted to the set A, where it's all xi, but they have to sum to t, right? So this is being restricted. But then this is the same, like if we call this f from the original x, but then have this extra requirement that t has to equal little t. Now, some take this and then write it as this product, right? It's just probability theory. And remember, t is a sufficient statistic, so there is no lambda in this, but the distribution for t has lambda. So this product, has lambda in it. And then that is our original distribution x, but it's restricted to, the set A, such that all the x in our sample have to sum to t. So this is like a little proof that we can generate data. Now, one note though, the way my mind works, I see this and go straight to here, right? But some like to go from here to here to here, and it's kind of a personal preference, but I personally make this link much, much easier than this step here. So let's illustrate auxiliary randomization, and let's continue our Poisson example. So let's let n be 2. So we take a sample size of 2, and since I'm doing this by hand, I wanted a small sample size. Let's assume our sufficient statistic, which is the sum of the xi, equals 3. Now, according to what we achieved up here, this conditional distribution is this. So we plug in the information. This is t, n raised to the t, and this is the product of our sample, factorial. And that you get that from above. So now let's fill out this table. So we need to find all the x's that satisfy t equal to 3. So you take all the x's possible from a Poisson distribution. Remember, x1 can be 0 to infinity, x2 can be 0 to infinity, but we have to restrict it to they sum to 3. So we go through each possibility. This is one, this is one, this is one, this is one. And that's all the possibilities we have. So now I'm going to build this up in stages. So the product of these, you know, from 1 to 2 of these factorials is, so it's 0 factorial times 3 factorial, which is 6, 2, 2, 6. And then NT, which is this piece here, so it's always 8. And then we take this product, you know, which is this bottom piece here. And so it's 48, 16, 16, and 48. Now the top piece, you know, 3 factorial is always 6. So then this density, you know, becomes this. So for this sample that, you know, that we could have collected, the probability is 1/8. This is 3/8, 3/8, and 1/8. So notice that there's no unknowns here. So we can use a random number generator and generate, you know, samples from the original distribution that, you know, from this restricted distribution that has the same distribution as the original. And so now, so if we only knew that n was 2 and t equals 3, we can generate data and then use that to create functions of it to estimate, you know, functions of the unknown parameter. Anyway, it's kind of interesting. This is a big area, auxiliary randomization. And but that's all we're going to cover for this playlist. And that's all I have for today. So hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.